Good afternoon. Thanks for joining us today. For the last several weeks, we've been talking about CAN networking. We started off with CScan, which is the Horner proprietary network, and we've transitioned into CANopen, which we've talked about last week and how it works. This week, we're going to do some hands-on with CANopen. And joining me, just like almost every week, is my good friend, Mr. Casey Gardner. How's it going today, Casey?
Hey, not too bad.
It's going well. You know, last week we had our live stream where we talked about how CANopen works. This week we get to get a little bit more hands-on, which is always fun. Now, last week, for those watching live, we had a little bit of a technical issue with your audio, but I'll raise my hand. That was all on my side. I totally screwed that one up. But anyway, what you tried to say last week was that you didn't have a ton of experience with CANopen. But you have had some for sure. What are some of the projects that you've worked on with CANopen?
Yeah, not a ton, and it's been a little while, but I think the last project I worked on was a servo drive that was also using a VFD for control as well. But that was definitely the last one that comes to mind.
Yeah.
What about you?
Yeah, I've done a ton of projects using servos, no question about that. I've done a couple VFDs, a variety of other devices. The one that was the most interesting really was an application where I got a call from a longtime customer who had a requirement on a machine for 6 encoders. And, you know, that's an unusual situation. And it wasn't really a motion control application either. So after giving it a little bit of thought, I thought really CANopen was the way to go. Sure enough, that's the way he went with it, and it actually worked out really well. So it ended up working quite nicely. So we've got an encoder that we're going to be showing folks how to configure later in the show, and we might even get around to a stepper drive as well. So should be a good program. Casey, as always, will be keeping an eye on the chat, answering any questions he can answer during the session. And then he'll be joining me once again at the end as we review any questions we have and he makes any corrections on anything that I've screwed up on, which happens from time to time. All right, let's go ahead and get started. Again, today's title, or today's session, if you will, is Hands-On with Horner OCS and CANopen. So let's go ahead and dive right in. So our agenda for today, we're going to start off with a quick review of CANopen. We're not going to spend a ton of time on it, but for those of you who haven't seen last week's session, we want to make sure we catch you up so you're familiar with the terms and what we're going to be reviewing. We're going to be talking about some great CANopen applications with OCS. We're going to be walking you through the configuration process, talking some about the diagnostics that are available, using some of it for, part of the demonstration, and then again, spending most of our time with actual hands-on with CANopen. All right, so let's start off with a quick review. Anytime you're discussing a CAN-based network, you really need to start with CAN. So what is CAN? CAN stands for Controller Area Network. It's a peer-to-peer communications network that's based on a standard chip. Now, billions of these chips are manufactured every year, believe it or not, in applications ranging from vehicular type applications like your car. There may be up to 50 CAN chips in your car, believe it or not. And of course, factory automation, which is our market, is also a very common application for CAN. Most of us are more familiar with Ethernet than we are CAN, so we always like to kind of compare and contrast the two. So CAN, because it was designed for automobiles and other harsh type applications, it does really well in those difficult environments with a lot of electrical noise, sometimes with tough environmental conditions. It's got a small code footprint, which means it can be used on even very small microprocessors. It does really well with error handling, and it has a lossless collision detection scheme, which means that even when you have collisions, a message always gets through. But it is limited in bandwidth. It doesn't have unlimited bandwidth, to be sure. When we take a look at Ethernet, it was designed to transport really massive amounts of data in a reasonable time frame. It has high bandwidth, which is great. But it does have a large code footprint, which means that it does take a reasonable sized microprocessor to work with it, and its collision detection is lossy. So you start having collisions and you start losing messages. You can see that CAN and Ethernet definitely have complementary strengths. Now, as we dive into CANopen, CANopen is one of the protocols that are built upon the CAN chip. Very popular in factory automation, and it was developed with motion control applications in mind, but it's certainly not limited to that. and it's got an administration called CIA, not that CIA, that is in charge of the specification. Now, although a lot of us aren't that familiar with CANopen, a lot of us who are Horner users are familiar with CSCAN. So let's compare the two. CANopen is a standards-based network. Okay, so it's designed for interoperability between manufacturers and for multi-axis motion control, or even single-axis motion control for that matter. It's highly capable, but it is highly complex. Whereas CSCAN, which is a Horner design network that's proprietary, was designed for efficient data exchange, I/O expansion, and ease of use. It's really a plug-and-play type approach. So they're really designed for two different situations. CANopen for multi-manufacturer support and motion control, CSCAN for peer-to-peer communications and plug-and-play I/O. So why would you use CANopen with one of the Horner OCS all-in-one controllers? Well, for the reasons that CANopen was designed. A need to add a third-party product from a different manufacturer, or a need to add a motion control style product to your Horner OCS application. Now, if you've got a simple I/O expansion requirement or simple peer-to-peer communications between OCSs, CSCAN is going to be a much easier approach than CANopen. But again, if you've got motion control in mind or a third-party device in mind, CANopen is certainly the way to go. Now, in terms of which Horner products support CANopen, pretty much everything from the XLE and XLT on up do support CANopen. It's not the case with the Micro series. That line does not support CANopen. Now, for all of our products that have a single CAN port, you simply need to download a free firmware update or upgrade to support CANopen natively in your OCS that has a single CAN port. If you happen to be using one of the models that have two CAN ports, like the XL7 or the EXL10 or the XL Plus, you simply need to select that second port on the standard unit with the standard firmware, and you're off and running. And then if you need to add I/O in an application with a single CAN port model, like an XL4 for instance, SmartRail is available with a CANopen base. So you will have the availability to not only support CANopen locally with a single port model, but also add some I/O via SmartRail. All the other Horner I/O platforms are only available with CSCAN. All right, now as part of our review, we're going to take a look at some of the key CANopen elements as well as protocols. And the first one we're going to talk about is the CANopen Object Dictionary. Now, if we think about the Object Dictionary, what this is, it's a list, effectively, of all the possible parameters that a device can share over CANopen. So whether it's an encoder or a variable frequency drive or a servo drive, every different type of device is going to have a certain amount of data that is accessible over CANopen. For those of you who've used Modbus with a variable frequency drive, let's do an analogy there. So if you've got a variable frequency drive and you want to be able to monitor faults and maybe change frequency or even start-stop over Modbus, the first thing you have to do is you have to pull out the user's manual for the drive and find out where all the parameters are mapped. Well, the Object Dictionary is the CANopen way of handling that. It's again a list of all the possible parameters that can be shared over the network. The listing happens to reference 16-bit hex indexes and 8-bit sub-indexes, if you will. CANopen also supports what they call device profiles, which means that if you are using a typical sort of device, like maybe a servo drive, like Casey talked about earlier, or an encoder, or maybe a pump or an RFID device, that there's kind of a standard profile already established by CANopen to try and make it easy when you have to use similar devices from different manufacturers to integrate them, because they work similarly, at least from a communication standpoint. So device profiles are certainly one of the more useful elements in CANopen, and since CANopen was developed for interoperability between manufacturers, that makes a lot of sense. Now, the rest of our review time, we're going to talk about CANopen protocols, the different types of messaging that are available with CANopen, because when we get into the configuration side of things, we need to have a working understanding of what these protocols are and what they do. All right, so there's 5 protocols we're going to be reviewing today as part of our preparation for our hands-on work. And we're going to start with Service Data Objects, or SDO type protocol. This is the protocol that CANopen uses when it makes occasional data access and parameter setting type communications. So if, say, you have a PID controller that talks CANopen and you want to do some tuning, and there's a tuning parameter you want to adjust, you're not going to be doing that all the time at runtime. You're going to be doing that occasionally. So using an SDO is a logical approach for that. Okay, again, SDOs are all about occasional data access. And they're a client-server type approach, or a master-slave is another way to think of that, which provides access to everything in the object dictionary. So if there's a parameter that's supported by your CANopen device, it's going to be accessible through an SDO. All right. Now, in terms of how the OCS products support SDOs, those are handled with function blocks. So we have an SDO read function block and SDO write function block, and you would utilize those in your logic in order to read and write SDO data on an occasional basis. And of course, you would use the user's manual to look up what data is available that you want to read and write over SDO. And then also CANopen supports something called an EDS file, an electronic data sheet. That's a pretty typical thing for a field bus. And in that EDS file, you will find a listing of parameters that are supported in addition to what other CANopen functionality is supported. And that's, again, a useful feature in CANopen. Now, we have the parameters and the communications that we'll do on an occasional basis. And then we have the other major form of communications with CANopen, and that's PDOs. So with PDOs, or process data objects, those are the continuous high-speed process data objects or process data that is read and written at runtime, again on a continuous high-speed basis. So every CANopen device, remember CANopen is based on CAN, which is inherently peer-to-peer, every CANopen device controls when their PDO data is transmitted. So whether it's a lowly, very small and expensive CANopen device that's very simple, it probably has control over when it is going to transmit its data. All right. So that's, again, another characteristic of CANopen is the fact that every CAN device, for the most part, has the ability to decide when PDO data is transmitted. Now, from an OCS standpoint, the OCS uses configuration to set up PDO data exchanges. So as an application engineer, you get to decide which data is important for the machine, which data you want to access on a read and write basis at runtime on a high-speed basis. And in the OCS, you can configure the entire network and configure all the devices on the network to provide the PDO information that you're interested in. So you have a lot of flexibility in terms of what data is read or written. And again, the EDS file is a valuable location, along, of course, with the user's manual, for determining what data makes sense for your application. So again, SDOs are occasional messages. PDOs are the runtime, all the time type messages. Now, another protocol we're going to talk about is network management. Without going into too much detail, network management effectively defines a state machine that's supported by all CANopen slaves or all CANopen clients. So every CANopen client at any given moment is going to be in a certain state, one of these states you see there in the diagram. And depending on the state that it's in, that's going to determine the sort of behavior that it follows. Now, the master, which is typically an OCS, is generally in control of taking the clients and putting them in a certain state. Ultimately, you want everything to be in the operational state. That's where all the messaging can be exchanged, including the PDOs. During the pre-operational state, if a network happens to be in that condition, at that stage, you're definitely not able to exchange process data. You can only exchange SDO data and some other messaging. So ultimately, the goal is to have the CANopen master put the network into operational state, including all the clients, so that PDO data can be exchanged and the machine can effectively run as expected. Another useful protocol to be aware of is called the heartbeat protocol. This is a protocol that's very simple. and it allows devices to effectively announce the fact that they're available. So an individual device will broadcast a heartbeat on a periodic basis, and some devices even have the capability of monitoring that other devices' heartbeats are active. Certainly the Horner CANopen Master that's built into the OCS can do that, and several other intelligent slaves can as well. Now, how is heartbeat configured? In the case of the OCS uses CANopen configuration to set up the heartbeat protocol. Now, if you do happen to have a slave that doesn't support the heartbeat protocol, and that's pretty rare, there's an older protocol that can be used for error control called node guarding. So you can always use that one as a backup plan if you have a particular client that doesn't support the heartbeat message, but that's pretty rare. Now, there's a couple other protocols that we're not going to go into too much detail upon because, frankly, they're not used all that often. The emergency protocol is basically a protocol that says that when a client has an error condition, it has the ability to send out a specific message that it broadcasts to the network that other nodes could receive and interpret. Again, even though that's useful, it's not used all that frequently. And then the timestamp protocol is a way of having the CANopen master typically broadcast network time down to the millisecond, and that can be used for timing purposes by clients on the network as well. But again, that's not that typical and isn't used all that often. So we aren't going to cover it in great detail today. Now, there is a special function protocol that is extremely useful, and that is the sync protocol. Usually, the CANopen master can provide a sync message that clients use to synchronize from. So the sync message is sent on a periodic basis, say every 20 milliseconds or 10 milliseconds, something like that. And then clients can then trigger either the capturing of input data or the writing of output data, as well as when to trigger their transmitting of their PDO data based on the reception of a sync pulse. And this is a highly effective way of synchronizing and coordinating multiple devices, which is one of the reasons why CANopen does so well with motion control centric type applications. And from an OCS standpoint, again, the OCS uses the configuration process to set up the sync protocol. So really, with the exception of the SDO protocol, which is done using function blocks, just about everything else in terms of CANopen setup and all the different CANopen protocols are configured using the configuration process in the OCS. Okay, so next we're getting right up to the point. We're going to start with our hands-on example of how to set up some CANopen devices, but I want to do a couple more slides just to talk about some configuration hints, some overall configuration hints. The key when you're configuring CANopen devices is to keep it simple. There are a lot of parameters, which you'll see shortly, and it can be intimidating. Keep it simple. Configure only what you need to. Get communication started, and then expand it from there. If possible, especially if you're just talking about interfacing with a single slave, adjust the master, which is the OCS, to the default settings of the slave. So if the slave has a default baud rate of 250K, consider using 250K. If the slave's default ID is 1, then don't use an ID of 1 for the OCS side of things. Adapt to the slave if you can, especially if you've only got a couple slaves that you're interfacing with. The other thing that will do for you is down the line, if a slave ever needs to be replaced, it makes it easier for a replacement to just come up and run. Another thing to keep in mind is that the OCS does not support a special protocol that's available in CANopen for auto-bauding. So because of that, you will need to use a fixed baud rate. You'll have to select that. So that's another hint. And then the biggest hint of all, probably, besides keeping it simple, is before you start, gather complete user documentation, which usually means the user's manual and very often a communications guide or a CANopen guide. Read through the information, understand what is supported by the slave and what is not. And then once you've done that, you're ready to start the process of configuring your system. Now, to expand a little bit on keeping it simple before we dive into the process, on the master side, or just in general, select your baud rate. Again, your baud rate is going to be based at least in part on what the default is for the slave. Also in part based on distance If you're talking about a 20-meter network or a 500-meter network, there's differences in terms of the maximum baud rate that can be attained. Map out your CAN IDs. Know what your slave defaults are, figure out an appropriate ID for your OCS master that's compatible, and take it from there. Again, after you've gathered up those EDS files, it's just a text file. Read through it, see what you can learn from that. And then you're going to want to copy the EDS file into the appropriate OCS directory, and I'll show you that here in a minute. Also, if the slave is intelligent enough where it requires some separate setup software, sometimes with variable frequency drives they have that as an option. If there's any setup you want to do in the slave, do that first. And then finally, on the CANopen master side of things, which is configuring the OCS as the CANopen master, set it up to handle the network state automatically. Configure up sync because it's so useful. Configure up the heartbeat function because it's the way you can detect that slaves have gone away. Now, with the data, the runtime data, remember that's PDOs. There's transmit PDOs that are transmitted by the OCS or the client. And then there's receive PDOs that are received by the OCS and the client. From an OCS master standpoint, you're only going to add your transmit PDOs after your master node number has been finalized, and that's because the address of that PDO will be determined by the master's ID. So if you're going to be changing the master ID at some point, you'd have to change all your transmit PDO addresses, and you don't want to do that after the fact. So just go ahead and set your transmit PDOs after you've established your CANopen master ID. And then on the receive side of things, for the data that the OCS is receiving in as the CANopen master, don't configure any of the receive PDOs until after all the slave transmit PDOs have been configured. So once again, for runtime data, only configure transmit PDOs after you know your network address, and only configure your receive PDOs after you've done the slave transmit PDOs. Okay, and then on the slave side, you're going to add the slave from the EDS file. There's no configuration needed for sync. You will need to configure the heartbeat. You will assign transmit PDOs if you can. So if there's a wizard that Cscape comes up where Cscape will say, hey, do you want to support transmit PDOs? And you absolutely should, for sure. When you do, you're going to not want to use global data references because, it's easier to use registers, frankly. So the slave wizard that I'm going to show you will ask you if you want to use global data references. Just refuse. And then if your slave supports receiving data, not all do, and the encoder I'm going to show you does not, if it does support it, then go ahead and say, yeah, I want to support those. If it doesn't, then you, again, refuse that. And then configure a single transmit PDO on your slave. Let's say if it's an encoder, I want to configure my position. And once I've done with that, configure the OCS master to receive that data in, and then test it. And that's pretty much it. So there are lots of steps there. It looks intimidating, but let's go ahead and dive right in. And I'll show you that it's really pretty straightforward. Now, the last thing I'll say is definitely make sure you take advantage of all the diagnostics that are available in the OCS so that if you do run into trouble, you can diagnose it quickly and take corrective action. Now, another thing I'm going to suggest is that a lot of times, instead of starting your CANopen configuration from scratch, it's a lot easier to start with a Cscape program that's already configured for CANopen, at least with a basic configuration for CANopen. And we happen to have some sample configurations that not only have just kind of a basic configuration already established, but that also have a whole bunch of diagnostic screens already built up, ready to go to make diagnostics even easier. So I highly recommend that. You can request a sample project from tech support. Just request one that fits the model that you're using. If you've got an XL7 project coming up, request a sample project for an XL7. If it's for an XL4, request it for an XL4, that sort of thing. Just to make sure that this, again, the screen diagnostics you're receiving are going to already be compatible with the type of screen that you're using. All right, so let's dive into our demo today. And I want to give a big shout out to Encoder Products. They provided as a loaner. They provided the CANopen based encoder for our demonstration today, and they're just a terrific company that I've worked with for a long time. Zach from Encoder Products is a guy that I have a lot of respect for, and a colleague that I've been working with for 20 years now. Well, more than 20 actually. So shout out to Encoder Products, and thanks for providing the equipment that we're using for our demo today. Okay, so let me show you what I have here. So what I've got is I have an XL7 with this sample kind of base CANopen project in it. And the first thing you'll probably notice, besides the big red light that says the CANopen network is not okay, is the fact that you've got this diagnostic screen already built up, which is really handy when you're starting a new project. Over here I have the Encoder Products encoder that is interfacing to CAN2 on this XL7, and this is the system that we're going to work together to get configured and up and running. So let me go ahead and let's head over to Cscape. And what I have is I have this sample program that I talked about that you could request from tech support. And what makes up this sample program? Well, if we take a look at the ladder, first of all, in the main ladder section, there isn't anything here because this is really designed as a starting point for a project, so there's nothing there. There is a CANopen section in ladder, which really all it does is interpret the CANopen status and then provide a couple of convenient pre-configured function blocks for reading and writing SDO data. And this can be done from the touchscreen because of the way this example was configured. The other big thing, which you've already seen on the screen and we'll review here in Cscape, is this nice diagnostic screen with all the different possible status errors that could occur, along with a numerical feedback for the slave status, as well as an indication of what state the network is in and if the network is okay or not. And then we've got another screen which is convenient for reading SDO data or writing SDO data on an occasional basis. So if there's a particular parameter in your slave that you want to take a look at and you want to do it from the screen, you can take the user's manual from that slave and you can look up the parameter, type it in here, hit read or write it if that's the case, and get that data. So that's pretty useful. So we're starting from this sample program. Now, one thing I want to show you before we get started is where to put the EDS file for the slave that you're working with. So let me minimize Cscape here and see if I can pull up the file system. And let me pull this up to the middle of the screen here. And if we go to this PC under the C drive and go to Program Files x86, which is where you'll find Cscape. Okay, so in the Cscape directory, you'll find an EDS folder. Double click there, select CANopen and EDS, and that's where you'll place the EDS file from the manufacturer that you're configuring. So you'll see here a whole collection of EDS files from different devices I've accumulated over the years. Okay, so that's where you need to put the EDS file. All right, back to Cscape. So I'm connected to this OCS that, like you saw, but I have not really done a full CANopen configuration. I'm just starting from the base here. So how do I get in and do the configuration? Well, let's go to the hardware config, and I can get there from here. And then let's click under CAN2, which is already set for CANopen. Now, like I mentioned before, the XL7, the EXL10, those products have a second CAN port which is configurable for different protocols, and CANopen is one of the choices. So that's what I'm going to use here. If I had an XL4, it only has one CAN port, so I would have to select CANopen from the pull-down list of CAN1. But here I'm using CAN2. So let me hit config. Okay, so this is the basic configuration that was provided with this example file. Now, I had mentioned in my hints that we should adapt to the slave's defaults if we can. Now in this case, the slave has a default ID of 127 and a default baud rate of 250K. Now the first thing you'll notice is that for the CANopen master, which is the OCS, we have a conflict already. All right. The default ID for the OCS master is also 127, so that's not going to work. So the first thing I'm going to do here to customize this particular configuration is I'm going to change the OCS ID to something other than 127. I'll just go ahead and pick 50. And I'm going to go ahead and adapt the baud rate to match that of the slave's default, which is 250. So I've done that. Now, also to take a look at how this is configured by default, the first checkbox you'll notice here is Perform NMT Start Node All. Basically what that means is the OCS is going to handle the NMT network state automatically by seeking to put all the slaves automatically into operational mode at startup, so you don't have to do absolutely anything in your logic to make that happen. So just make sure that box is checked. All right. Now there are plenty of other things that can be configured in CANopen, and my hint to you was, let's keep it simple. Under device type and status, there's nothing to configure. Under special function objects, you'll notice that the sync message has already been configured. All right, I didn't have to change this address, that's just the default address, but it was already set to generate the sync message, so the OCS will generate the sync message. Now, how often will it do that? Well, through this setting right here, and it looks like it's set for 20,000 microseconds, which is 20 milliseconds. So every 20 milliseconds, the OCS is going to send out a sync pulse to the network that the slaves can use if they choose to base their data capture and to base their PDO transmissions on. And then there's one other thing to talk about, and that is the synchronous window length. What does that mean? Well, that's a shorter period of time. That's shorter than the 20 millisecond sync generation time, in which as long as the slaves respond with their PDOs, their synchronous PDOs, within that time frame, then everything is good. So in this case, I've got that configured for 10 milliseconds. So we'll be sending out a pulse every 20 milliseconds, and we'll make sure that all the slaves respond within 10 milliseconds to that sync pulse. Okay, but again, this was pre-configured in the demo file. I didn't have to do anything here. So that was under special function objects. Under error control, remember the error control protocol we typically want to use is the heartbeat protocol. And we're set up to automatically generate a heartbeat every 500 milliseconds. So that's great. That's pretty much done for now. Now, once we add a slave in, at least one, we'll also want to set up a consumer time, the time in which we're willing to wait for a heartbeat message to come in before we flag an error. But we can't do that until we've already configured a slave. And then on the PDO basis, on the transmit PDO and the receive PDO basis, we can't really configure any of these until we've handled it on the slave side. So these are going to remain blank for now. So let me go ahead and collapse this down. And now we're ready to add our slave, our encoder. A couple ways you can do that. You can hit the Add Slave button, or you can right-click under Master and hit Add New Slave Node. Got it? Okay. First thing it asks for is the ID. What is the ID of the slave? And I think I mentioned before that the default ID for the encoder is 127. Now, we may have decided in the application that we're going to use a different ID for the encoder. So if that was the case, we would have need to have changed that ID by now in the encoder through some sort of process, whether that's through software or by sending a STO, occasional message, to a specific address to change its ID. But in this case, to keep it simple, we're just going to use the default. All right, and we always want to load from EDS as long as we have an EDS available. I'll hit Next. Now, I had mentioned we're gonna check as few checkboxes as we can, and the sync really only needs to be configured on the master side. So there's no need to check that one. We aren't using timestamp. We're not using emergency. Okay, so we're going to leave those all unchecked. We are using heartbeat. So we do want the slave to produce a heartbeat, and 500 milliseconds is a good time. And the slave really should also check for a heartbeat from the master. What's the master number? Well, we're node 50, remember? Okay, it's going to check a heartbeat from node 50 every 1 second. You always want to consume heartbeats at a slower rate than you produce them. That way, or that they're produced. That way, if they're delayed just slightly, you don't see it as an error. So there's a good setup for the slave. Generate a heartbeat every 500 milliseconds. Check for a heartbeat from a master every second. All right. The node supports the SDO server access with default object IDs. Absolutely, we always want to use default IDs if we can. Enable transmit PDOs. Now this is an encoder. It definitely does transmit data, so we do want to enable those. How do we want those to be transmitted? Remember, the slave is always in control of when it transmits its data, although the master can tell the slave how it wants it transmitted through configuration. That's what we're doing now. So let's go ahead and make the default method of transmission synchronous, okay? And then number of transmit PDOs. Now the maximum number allowed is going to be determined partially by the slaves, well, fully by this, what the slave can support. So that's another reason to read the user's manual for the slave. In this case, I'm going to go ahead and configure 2 transmit PDOs, which can be supported by the slave. We're always going to use default object IDs. Anytime we have the choice, we do that. And I mentioned in my quick start that we typically avoid mapping any kind of PDO data to global data. Ours are just simpler. General purpose register data is just simpler. Now, this is where we can enable receive PDOs if the slave supports them. In this case, it doesn't. So we're going to go ahead and leave that blank and hit finish. Now, when we hit finish, this is where the specific EDS file for the slave that we're dealing with can be selected. So we're dealing with an encoder products product. Now, they don't happen to be the original manufacturer of it. In this particular case, they manufacture almost all of their stuff, but in the case of their CANopen option, it is a partner product, so we'll select that here. That's from Wackendorf. All right, and we have 1 device to choose from and 1 profile to choose from. It calls up our CANopen file. We hit OK. So now we're ready to start configuring the slave. All right. We've had a wizard that's helped lead us through the process. Now let's go through and just finish up the configuration. Again, my hint to you is the simpler the better. So we're not going to check any of this stuff up here. All we're going to check to keep things simple is configure the error control protocol, which is heartbeat, and configure the slave's PDOs and SDOs. So that will give us as the master the ability to determine what data we want the slave to broadcast as process data. And as an application engineer, that's pretty powerful. So that's all we're going to configure on this particular page. I'm going to go ahead and expand the slave configuration. Nothing can configure under device type. Under special function objects, remember, all of our configuration for sync at least was done on the master side. We're not supporting timestamp. We're not supporting emergency protocol. Under the error control object, the wizard kind of walked us through the process of producing a heartbeat every 500 milliseconds and consuming the heartbeat from the master, node 50, every second. So that looks good. All right, there's nothing to configure under SDOs. Now all we have left is configure our PDOs. Now I'm going to briefly take a break from the PDO process to go back to the master and configure its heartbeat on the consumer side. Oh, it's already there, except it set a limit that I'm not thrilled with. I always want to consume a heartbeat at a slower rate than it's produced. So I'm going to go ahead and modify this, not for 500 milliseconds, but for 1,000 milliseconds. All right, so again, I'm in the master configuration for error control, and I just made sure that not only am I producing a heartbeat at a compatible rate with what the slave is expecting, it's expecting it every second, I'm transmitting it twice that fast, but also that that the opposite is true. I'm consuming the slave's heartbeat at a compatible rate. Let's go ahead and recompress the master and go back to the slave. So we've configured everything except for our process data objects. This is, again, the runtime data that we are going to transmit and potentially receive, although as an encoder, this device doesn't receive, it only transmits. So we are right now to the point of configuring our transmit PDO. Now, when we went through the slave wizard to add our slave, we said we wanted to support 2 transmit PDOs. So it established these for us automatically, okay? And up here, this is where you have configuration for when PDOs are generated. okay, what their address numbers are and when they're generated. It doesn't configure what gets sent. All right, it doesn't say what data gets sent, only when. So let's double click and take a closer look. We've got the address of the first PDO, which is same as the default. We never mess with any of the defaults when it comes to addresses with CANopen. In this case, it's set to transmit on the sync pulse. All right. For the purposes of this demonstration, I'm going to illustrate how you don't always have to transmit PDOs on the sync pulse. You could be a slave that has some data that needs to transmit on the sync pulse, but other data that maybe should transfer another way or be transmitted another way. So for this first PDO, I'm going to change from synchronous to asynchronous, and I'm going to set it up for on change. So what that means is, now that I've made this change, this encoder is going to transmit its first PDO, its first output process data, not on every sync pulse, but whenever the data changes. All right, now I have the potential, if the data is continuously changing, of overwhelming the network with traffic. So there's this inhibit time parameter that I could set, say to 100 milliseconds or 500 milliseconds or 20 milliseconds, that would prevent me from sending another PDO if I have recently sent a PDO in that time. But for the purposes of demonstration, I'm just going to leave that blank for now. Okay? So again, this first PDO I'm going to transmit, or the slave's going to transmit on change, not on the sync pulse. Now, the second PDO, let's go ahead and leave it at the default that was established of transmitting it on the sync pulse. So we'll leave that alone. Again, we have not determined what gets sent, only when. So I'm going to highlight this first transmit PDO, and down here is my mapping area for mapping the data from the slave that's going to get generated. I'm going to go ahead and hit add entry. And when you're talking about slave PDOs, it's all about the EDS file. One of the things that makes things nice is the EDS file. So we ignore the rest of this stuff for now and go straight to set from EDS. This pops up all the data that is available to us to be transmitted. So let's find what we're looking for. Now this is an encoder. Let's go ahead and just select the standard position value, which is an unsigned 32-bit read-only value. The unsigned 32 is important to note. So once I select that, I need to select unsigned 32, all right, and say OK. And now I have my entry of what gets transmitted with that first PDO. It's going to be the position, which is an unsigned 32-bit value. Now, each PDO can be as large as 8 bytes, and 32 bits is 4 bytes. So if I wanted to, I could add additional parameters to this same PDO that are being transmitted asynchronously. But in my case, I'm not going to. I'm just going to go ahead and leave it alone for now. Now let's select the second transmit PDO, the one that's sent synchronously, and let's add an entry for that one. And in this purely academic exercise, although we are going to see values when we're done, I'll go back to set from EDS, and I will once again select the same parameter, position value, but we're going to be broadcasting on a synchronous basis instead of asynchronous this time. All right? All right, so from a slave standpoint, I'm pretty much completely done, at least from the standpoint of my initial test. I have verified my heartbeat. I have checked as few checkboxes as possible, frankly, and I have configured at least one transmit PDO that I can use to test things with. However, what that transmit PDO does is it really just sends data to the network. It doesn't perform all the configuration that's required for the OCS to take that data from the network and map it into local memory. To do that, I need to go back to the master configuration, which is the OCS, of course, expand that, and go to the receive PDO of the master. Because remember, we're talking about data transmitted by the slave that needs to be received in by the OCS. That's why we're talking about receive PDO. Now, unlike the slave, there are no default PDO entries already in here. So I'm going to go ahead and add an entry. All right, and when I do that, when I hit that Add Entry button, it pulls up with a list of all the transmit PDO data that's out there that I could choose from. And these are the two that I've just configured, the asynchronous and synchronous ones. Now, here's something that can throw you off, and this is a little bit unfortunate on the Seascape side. You'll see here, these are listed under slave 2. The 2 does not refer to CAN ID of 2. It refers to the fact that it's the slave that is second on the list. The master is first on the list, and in this case, this slave is second on the list. So that's the slave that's being referred to here. That really probably needs to be cleaned up on the Seascape side. But let's go ahead and select the asynchronous PDO that we want to map to, because remember, we're coming up with a receive PDO on our side that we're going to receive in from the OCS, or into the OCS, and that data needs to be mapped from a transmit PDO, and we're going to select the first one, and then we'll add another entry and select the second one, because we'll go ahead and do them both. Now, by default, when you add an entry to a PDO table, it always comes in disabled. So don't forget to uncheck that checkbox so that PDO will not be disabled, because that wouldn't work if we did that. Okay, now we're going to highlight that first PDO, the asynchronous one, and we need to tell the OCS where that data needs to go. Remember, that's the position data that's coming in asynchronously. So let's add an entry down here. Now, I talked about the fact that with the slave, when you're adding in PDO data, it's all about set from EDS. With an OCS, it's all about the register address. You ignore everything else just about. In this case, I want to put, and this is where you have the choice as the application designer of where do you want the data to come in into the OCS memory. In this case, I've set up this application where it's looking for the asynchronous position to come into register 8001. I need to make sure I get the data type right, unsigned 32. Okay. And as I select the second receive PDO and hit add entry, I want the second one to come into R8003. All right. Again, unsigned 32. And OK. So I'm now completely configured. All right. Everything has been configured, and I'm ready to download it and give it a try. So I'm going to hit OK here and OK again. I'm going to go ahead and hit download and OK. All right, now this is the initial download, or I guess it's not the initial download. This is the download where Seascape has to figure out what it is specifically that has changed, and so that's being downloaded now. All right, let's switch over to the overhead view of the OCS while this configuration is downloaded, and let's take a look. Hey, the first thing we should notice is we have a green light here under CANopen Network OK. Good news. Okay, and over here, if we take a look, this is where our data is copied. I happen to set up this screen to copy in the encoder position asynchronously and the encoder position synchronously. Now, why is this one at a 0 and this one has what looks like a more realistic position? Well, here's what's going on. Remember, with asynchronous data, it only gets broadcast by the encoder when it changes. And ever since we started this demo, the encoder has been sitting there idle, so it has not changed one bit. Whatever position it was at before, it's still there. Whereas, ever since the CANopen configuration has been downloaded, the OCS has been generating sync pulses, and the encoder has been receiving those sync pulses and responding with its current position based on receiving the sync pulses. So that means that for now at least, the data that's being generated by the sync pulse has come through the network. The data that's being generated on change has not. So if I do a little bit of turning here, now we go, you can see that we're good to go. So now, once things start changing, our asynchronous data catches up with our synchronous data, at least from the standpoint of the OCS registers. Okay, so that looks good. Now let's see what happens, because we did such a very basic configuration. Let's see what happens when we unplug the network. Let's see if we get an error and what it looks like. Okay, I went ahead and pulled that. Okay, so sure enough, we do have a couple errors have shown up. Our CANopen network is no longer okay. And while it may be hard to read on the screen here, we've got 3 different errors that have flagged: a transmit error, a consumer heartbeat expired error, and a slave error. So those all make sense. And in the upper right-hand corner, we have some additional diagnostics that if we look up in the help file, we see that we have an error code of 11 from slave number 127, which if we look that up, it says that that the slave has failed to generate a heartbeat. Makes sense, right? If it's not physically connected, it can't do a heartbeat. All right, so I'm going to go ahead and plug it back in again, and let's see if it recovers. Again, we've got a very basic CANopen configuration here, and it's not recovering. So that means we're going to need to add a little bit more to our configuration to make sure that we have a little bit more of a robust system than what we've got currently. All right, so let's go back to Seascape and let's take a look at a simple thing we can do to alleviate that issue. All right, so I'm going to go back to the CANopen configuration. All right, CANopen config here, and I'm going to go to the slave configuration, the main screen here, and up in this corner, I'm going to go ahead and check this box right here. On error, start the boot sequence. By checking that checkbox, what should happen is that whenever a slave sees an error, it should be prepared for the master to be bringing it back online. Okay, so it's going to be effectively preparing itself for going back online by entering into the boot sequence. So I think that will probably take care of what we need. I've checked that checkbox. Now we just need to do another download. Okay, download. Seascape is figuring out what has changed. And then once it comes up with that checkbox, it will go ahead and download only that portion of the configuration. There it goes. We'll go back to the overhead view of our OCS. And once again, we're up and running. Once again, our asynchronous data has not caught up with our synchronous data until I turn something. There we go. I will go ahead and pull the network. All right, and my CANopen status has gone offline. All right, and my errors are coming in. Yep, there's that heartbeat error. And one thing you'll notice is that the OCS is attempting to reconnect with the slave, and it's getting some variety in that error code now. But now let's plug in the network again, and let's see if it recovers, and it does basically right away. So it has immediately recovered, and away we go. All right, so now we have not only a simple configuration, but a more robust one at that. So hopefully that will give you a good handle on the general process that's required for configuration. And yeah, there's a lot of steps, but if you keep it simple, then it's something that, you know, is not that onerous. You know, we do a lot of complicated things as just automation designers, and this is something certainly that with a little bit of preparation we can handle, and the benefits are huge. Not only for applications where you need to add an encoder, but let's say you need to add a stepper drive or a servo drive or something of that nature. CANopen is a terrific option, and it can be very inexpensive. You can easily add several stepper drives or servo motors, integrated servo motors, you know, to an XL4, for instance, very economically, and have a really well-performing system, you know, for doing things like indexing, you know, moving back and forth, that sort of thing. Of course, you can always use step and direction, but that's a little bit old-fashioned, and you get a lot more control and a lot more functionality using CANopen. Okay, so I'm going to go ahead and let's go back to the slides. I think I've pretty much covered that information. Again, a big shout out to Encoder Products for providing the equipment that we needed. And let me go ahead and bring Casey back in here. Okay, Casey, were you able to follow along okay with that demonstration?
Yeah, I think so. Everything went pretty good.
Yeah, I mean, if you're careful about it and just change one thing at a time, and you start with a basic configuration, you know, that makes all the difference in the world. And another thing that makes the difference, to be honest, is starting with a program that already has the CANopen status information populated on the screen. It just makes troubleshooting really simple. The alternative to that, of course, is getting the information out of the help file, which is all there and available. But by having the information already on the screen, with flags already set and ready to monitor. Again, it just makes things that much simpler. So putting in the work ahead of time, or better yet, getting the example program from our applications team is a good way to get things started.
Sounds good. We'll have that in the link as well, right?
Not today. Later on, yes. If you're watching this on replay, I'm sure we'll have that in the link. I don't think it's in there in the live stream yet, but we'll get it added there. The one that I went through, the XL7 kind of base configuration program, we'll go ahead and get that linked in, shortly after the live stream's ended. Okay. So, anything else came up, Casey, while we were giving the demonstration?
Don't think so. I don't think we had any questions come through, so you did too good of a job there.
All right. Well, I will mention that every Tuesday we have a live screen, not just this Tuesday, of course. And don't forget to join us. It's 2 o'clock Eastern, once again, every Tuesday. And next week, we've got what we think is an exciting one. So for the last 4 weeks, we've covered CAN topics. Next week, we're talking about the new Horner app for Android. So I'm sure many of you who are watching this have seen the fact that we have had for about a month or so, maybe a couple months, we've had a Horner app for iOS that allows you to, manage WebMI nodes, allows you to, manage FTP and WebMI type credentials. It's a really useful, simple application. And now we've got the same thing for Android. Very exciting. So as I bring Casey back in here, you're an Android guy, aren't you, Casey?
I have both at the moment.
Outstanding. So
I have one of each.
Very good. And I believe you were one of the ones that were involved on the Horner side in testing out the Android app. Is that correct?
I am. I'll pull it up here and show.
All right, very good. Nate Beachy, who joined us while you were off for a couple of weeks. He also is an Android guy, so he was another one of the testers. That's just a quick preview there, just to whet your appetite. So don't forget to join us next Tuesday for what we think is going to be a fun session where we show you and show off the brand new Horner Android app. Okay, once again, thanks for joining us. We'll see you next Tuesday. And if you have any questions whatsoever, even if you're watching this on replay, don't hesitate to type those questions in the comment section below the video, and we'll see that you've added that question, and we'll get it answered in a timely fashion. Once again, thanks for joining us.